Let us now take a look at our definition NU and extract a different flavor, a different color from the definition. It's a variation on that theme, this time taking into account conditional information. Recall that the idea of conditioning effectively reduces a sample space to the space governed by the event described in your side information. No new concepts are needed to describe independence with regard to this new foreshortened smaller sample space. So without any further ado, here is now a definition of conditional independence. So we'll say that two events A and B in some probability space are conditionally independent given an event C of some positive probability, if indeed a rule of products emerges for conditional probabilities. The probability of A intersection B, given that C has occurred, is equal to the probability of A given C times the probability of B given C. Again, let me re-emphasize that no new ground has been covered here. This is exactly the same old idea of independence as a rule of products. In a conditional setting, we are taking into account the fact that conditioning on the occurrence of some side information C, some event C, effectively has reduced the sample space to C. And then all event probabilities are now reflected into C. Independence in that context, again, is just a rule of products. Now, let me immediately give you an example of a common setting where this kind of conditional independence arises naturally. Again, we go back to coins. So, the setting is as follows. Imagine that now we have two coins. A coin, say coin 1, very creatively called, whose success probability, the probability of a head, is 1 in 6. And a second coin, creatively coin 2, whose success probability, the probability of a head, is 5 in 6. The first coin is weighted away from heads, the second coin is weighted towards heads in these proportions. We select one of these two coins at random. We are equally likely to select one coin or the other. Having got the coin, we pick it, put away the other coin, and toss the chosen coin twice. Okay. What is the probability space that is appropriate for this problem? As always, we'll begin with the sample space. The sample space, recall, to identify what this is, we're going to have to track down all sources of uncertainty in the experiment. Let's do this systematically. First, there is an uncertain selection of a coin. There's a coin choosing mechanism. Good. Having specified a coin, there are two tosses. So naturally enough, if I specify a triple, the selection of the coin, the result of the first toss, the result of the second toss, I will have completely eliminated all uncertainty in what happened in this experiment. The sample space, therefore, is a space of triples specified by a coin selection, coin 1 or coin 2, followed by the results of two tosses, heads or tails, heads or tails. Excellent. Let's put some events of interest together. So let's start with some very banal and simple events. Say A is the event that the first toss of the chosen coin results in a head. Let B be the event that the second toss of the chosen coin also results in a head. Now we want to say something about A and B, right? But the structure of the problem makes clear that an ancillary event might be useful. And which ancillary event? Naturally, the specification of the coin. Let C be the event that the coin chosen is the first coin, coin 1. Of course, the complement of C is the event that the coin chosen is the second coin. Now, what is an appropriate probability measure for this problem? Now, I'm going to pose it for you that there is indeed a natural probability measure. And that measure says that conditioned on the choice of the coin, if I chose the first coin, then the chance of getting a head on that toss of that coin is 1 in 6. And this chance is unaffected by the number of tosses. Mathematically, we want to put all this verbiage into a succinct encapsulation. And what we're really saying is the probability of A given C, the probability of a head given that coin 1 is chosen, is 1 in 6. And this is the same as the probability of a head given that coin 1 is chosen on the second toss of that coin. So far, so good. How do you put the two tosses together? Now, the moment we think about flipping a specified coin again and again, we want to model that these successive tosses are independent. Okay, I'm using the word loosely now, but what is the formal structure? This means that the results of each toss don't affect the results of other tosses. Formally, this means there must be a rule of products. And what we're saying then is the chance of getting a head successively on two tosses of this chosen coin 1 must be governed by a rule of products. And therefore, the probability of A intersection B of getting two heads in a row, given that coin 1 is being tossed, must be, if there is any justice in this world, the product of the corresponding probabilities. But each of the probabilities is 1 in 6. And therefore, the chance of two heads in a row for coin 1 should be 1 in 36. Observe that in the specification of this problem, it is implicit and natural that the events A and B are conditionally independent given the choice of coin. Of course, you verify that given C complement, again results in independence for A and B. In this case, I'm tossing the other coin. And the chance is now going to become 5 in 6 times 5 in 6, or 25 over 36. Well, so here's a natural setting where conditional independence arises naturally. Before we move on, we should pause and say, well, what can I say unconditionally about the events A and B? At the moment I start thinking about this, you realize, well, gee, we have a bit of a problem here. What is the probability of the event A that the first toss results in a head? But A says nothing about the chosen coin. So it could be that I chose coin 1 and I got a head. Or it could be that I chose coin 2 and I got a head. Which of these two cases? Well, this is not specified a priori, but implicitly here is a natural partition for the problem. The event C partitions the space into two pieces, C and C complement, and therefore total probability, additivity of probability measure, allows us to stitch together a chain for the probability of A involving the conditional probability of a heads given the particular choice of the coin. But here we know all the parameters. The probability of A given C is 1 in 6. The probability of choosing coin 1 is 1 in 2. The probability of A given the complement of C is 5 in 6. The probability of choosing coin 2 is 1 in 2. And the fractions assemble, collapse, and give you back 1 in 2. Pause for a moment and say, did I expect this? And some introspection might convince you that in fact this was to be expected because there's such beautiful symmetry. Chance 1 in 6 and 5 in 6, chance 5 in 6 and 1 in 6, that on average I should get exactly the midpoint. Nice and beautiful. What about the event B? Well, a little thought will show you that the analysis is exactly the same, and therefore the chance that you get a head on the second toss of whichever the chosen coin is by total probability is again 1 in 2. What about the probability of A intersection B, that the first and the second tosses result in heads? Again, we are naturally going to condition upon whether we choose coin 1 or coin 2, and total probability gives us an identity. The probability of A intersection B conditional on whether coin 1 was first chosen or coin 2 was first chosen. And now we simply write out these probabilities. Remember that A and B are conditionally independent given C or given C complement. Given C, A and B have a chance of 1 in 36. Given C complement, A and B have a chance of 5 squared over 6 squared or 25 over 36. Assemble it. Put it all together and we've got a simple identity. Simplify it, massage the numbers, and we get 13 over 36. Now the actual numerical value makes little matter here. The question at heart that we're going to ask is this: are A and B independent unconditionally? Well, naturally, we need to check a rule of products. Is it true that we have a rule of products, P of A intersection B is equal to the probability of A times the probability of B? Well, the probability of A times the probability of B is 1/2 times 1/2, which is a quarter. And that is manifestly not equal to 13 over 36. And therefore, the probability of A intersection B is not equal to the unconditional probability of A times the unconditional probability of B. And we conclude that A and B are not independent unconditionally. There's a slogan we need to extract from this. Okay? And what is the slogan? That independence can affect things in unexpected ways, and that in particular, conditional independence does not imply unconditional independence, or vice versa.